Last time we were working in section 15.2, and I believe the last thing that we had done is that I had introduced the evaluation theorem 2.4. And we talked about working on line integrals, and we had talked about evaluating these, and each of these equations, of course, is quite similar, but based on whether or not we're taking the integration with respect to x, to y, or to z. So we're going to do an example next with one of these where we're finding the line integral not with respect to surface or arc length, was what we were doing last time, right, with respect to arc length, but now with respect to one of the particular variables, x, y, or z. All right, so what we're going to do is we're going to be finding the integral over the curve C of the sine of x squared plus z dy where C is the portion of y equal x squared in the plane z equal 2 from 1, 1, 2 to the point 2, 4, 2. So z obviously is not changing because we're in the plane c equal to 2. So in a very real sense, the values that are actually changing is that we're going from 1, 1 in terms of y, because we're staying in the stationary plane, to 2, 4 in x, y. All right, so do you remember how we were doing these? I know it's been like 5 days. What were we doing when we were first looking at finding these line integrals? What did we have to do?
Find an x-equal equation.
Right. We had to do we had to parameterize things, right? We had to find parametric equations for x and for y. So one of the nice things that we did before is we were working with line segments. This isn't a line segment. This is actually a curve, correct? But it's nice in the sense that we actually have an equation for the curve. So that's helpful. If we can give a value for x, for instance, we can know exactly what y is because we've got an equation that determines how we get from x to y. Okay? So we're going to start there. And this is one of those ones where it's a very natural parameterization. So we don't have to do anything sort of fancy to get it to work for us. We're simply going to let x of t be equal to t, which means then that y of t is what? T squared, and then we have to figure out what the parameter limits are on t, okay? So what is the minimum value and the maximum value on t in order for us to start at the ordered pair 1, 1, so to speak, and end at 2, 4? Right. Lower limit of 1 and upper limit of 2. In a very real way, you can base that on just the particular x value because we were letting x equal to t, right? So this is the first one that we have encountered where we're not going to go from the integral from 0 to 1. Our integral is actually going to go from 1 to 2. You guys catch that okay? Okay, just because that's the natural way to do it. Are there other ways? Could we have gone from 0 to 1? We probably could change this, but there's not a need. We get to pick those anyway, so we're going to pick something that's going to work easily for us. Okay? All right. So our integral is going to go from 1 to 2, as we said, of sine. Oh, there's one other thing I want to make mention of. Let's come back over here to this equation. So which of these three are we going to be doing for this equation, or for this problem? Are we going to be doing which of these three integrals?
dy.
We're going to be doing dy. Okay? What I want to point out in this particular well, I guess they do it differently. That's fine. Okay, so we're going to be doing dy. Yeah, that's fine. We'll start here. So our sine value is supposed to be x sine of x squared plus z, Well, x is t, so that's t squared plus, and then z is actually what? 2, because we're stuck inside of the z equal to 2 plane. So we can actually just let the z equal to 2. And we're doing this with respect to dy, right? All right, so what's it say we're supposed to do over here? Well, we're supposed to find the integral in t. We are going to have a dt, so I'm going to change that dy and the n to dt. And what goes in the place right there for the dy? Y prime. I actually need to know what y prime is. So, taking a look at the equations that I have created, what is y prime? 2t. So this problem right here can be rewritten as the sine of t squared plus 2 times 2t and then dt. Is everybody good with that? If you look at this one in your book, they actually keep the t out of it and they just put x's in for everything because t and x are the same thing, just so you're aware. I mean, it doesn't matter which letter we're using, but they actually used the x on this particular example when they were creating the solution for it. But all right, so we need to do an integral for this. How are we going to do that? U substitution, what's u going to be?
T squared plus 2.
Right, t squared plus 2, which is fabulous because du is 2t dt, right? And we have that piece right here. So if you want to rewrite, I know some of you are sort of beyond that in your mathematical thinking and you can just move straight forward, which is fine. If you want to rewrite that too, then this would just be sine of u du. So what's the antiderivative of sine u? Negative cosine of u. And our u value is actually t squared plus 2, right? So this is the negative cosine of t squared plus 2. And the t values are supposed to be going from 1 to 2. So 2 down to 1. And we're going to evaluate them. So what do we get when we plug in 2 here? Negative cosine of 6, and then minus the negative cosine of 3. And cleaning up just a little bit, this then would be the cosine of 3 minus the cosine of 6.
Do you not want us to approximate?
You can leave it like that. You can get a decimal approximation as well. So I want an actual answer at some point in there. The decimal approximation is your choice. If you were working with an application of something, of course, you would want a decimal approximation. If you'd like to get one here, you can. James, you've got a calculator out for us. Can you find us a decimal approximation for cosine of 3 minus cosine of 6? Fabulous. So it was approximately negative 1.95. Any questions? Okay. All right, so the purpose in finding line integrals with respect to the 3 coordinate variables is to compute work done by a force field. That's why we're doing it, okay? So the work done by a force field while an object's moving along a curve. And they actually derive how this formula, I'm just going to tell you the formula. The derivation for this formula is on page 999, for real, 999 is where this formula is sort of derived. But the formula for work over a vector field looks like this. It's the integral over our curve C of our equation F. It's a vector equation, right? It's a vector field with input variables x, y, z. This is the dot product with dr. And please write that down. I don't want you to think that this is multiplication. I mean, that's not, multiplication is part of what dot product is, but this isn't just the normal dr at the end where it's a part of taking the limit of integration. This is the dot product here. So we will have to treat it as such. All right, so we're going to do an example of how this works, of course. We're going to compute the work done. By the force field F. Along the curve C. The example we're going to work with is the force field over xy of y squared plus x y squared plus 2, and C is the quarter circle from 4, 0 to 0, 4. And naturally a picture is in order to do that. So 4, 0 is here, 0, 4 is here, and here's the quarter circle that we're going around. All right, everybody good so far? So the way that we've done all of these is we've parameterized our curve to start with. This shape lends itself very well to telling us what our parameterization should look like. Do you remember what we did with parameterizations when we have a curved shape like a circle? This is a portion of a circle. Right. X equals R. And what is R here? Maybe I should actually say that. 2. Our radius, how about 4? 4, yeah. I bet, right? I mean, I was right there with you, 4. 4 cosine theta. And then y would be 4 sine theta. You can use theta if you want to use the t that we've been using before as well. You can use t. I'll leave it as theta just because we already wrote theta down. And what is my theta limits of integration that we're going to be using here? Right, 0 to pi over 2. And part of drawing our picture is for the purpose of being able to write that down easily, of course. All right, so what we're trying to do is we're trying to calculate this work equation. Let me actually write it in here the way I had it on the previous slide, since this is the first one we have seen like this. We're supposed to be doing, and this is just x and y because our force field is only in terms of x and y. And then I've got this dot product with dr. Okay, so for our equation, ours, I'll just put C for now, is supposed to be taking each of these components. So the first component was y squared plus x, and the second component was y squared plus 2. And what a dot product does is it dots it with the opposite, or not opposite, with the dy dx of the component. So this dr right here at the end, let me write it in. Dr here is dx dy. So when we do the dot product, we do the first components times the first component, and the second times the second. Do you guys remember that from dot products? That was last semester stuff, right? Okay. So, I'm sorry, I didn't finish out the other one yet. And I'm running all sorts of my stuff into things. So I think I need some parentheses right here, and then dy. A little bit better spacing. So this is what we're working with. And we're going to parameterize it. Okay? So far so good? All good? Okay. So we will have this values on theta to go from 0 to pi halves. Our y value is 4 sine theta. So this would actually give me 16 sine squared theta. My x value is 4 cosine of theta. And then I'm supposed to do dx. So let's take a look back over here. What is dx going to be? Negative 4 sine theta. Good. And I'm going to need it in a minute, so we'll do it while we're here. What is dy? And I put the d theta on the end there. I'm sorry. And then what did you say, James?
4 cosine theta d theta.
4 cosine theta d theta. Okay, so I've run out of space. So let me move this down just a little bit so I can continue it. All right, and then this is supposed to be times dx here. So this is times negative 4 sine theta d theta. That's the first half. And I need this plus, and I have y squared. Okay, well I already did y squared, so I know that's 16 sine squared theta plus 2. And then times dy, and dy was, where did I write it? 4 cosine theta d theta. Does all that look okay so far? Look at all that wonderful trig going on. We're going to have several lines of cleaning up some trig now, aren't we? Probably so. All right, so let's take a look at what we've got. All right, so let's distribute things and simplify what we have. I have sine cubed, I think, yes? And is it negative 64? Negative 64 sine cubed theta minus 16 sine theta cosine theta plus, startled me too. All right, what do I have next? 16, there's another 64, right? 64, and then it's sine squared theta cosine theta. Oh man, I'm so close to fitting it all in one line, aren't I? Just learned to write a little bit smaller. Plus 8 cosine theta d theta. I think that matches my notes, so I think we got it all okay. All right.
You just took the d theta, factored it out.
Yeah, I just factored the d theta out exactly. Yeah, and we often get sloppy, but the reality is, of course, that you guys recognize that all of the d theta applies to all of this. So we don't usually write that at this point in mathematics. We're a little bit more particular about it when we first do it in Calc 1. But all right, now what? Give me a suggestion. What would you see that we could do? I mean, there's nothing that directly combines as it's currently written. So now what?
Put it in the calculator. Wolfram alpha.
Oh, come on. You guys know some trig stuff you could do.
Pull an 8.
Okay, that's true. You could. That's not trig. Yes, we could pull out an 8.
Well, you can do use substitution.
You can have to like.
Okay, so
Yeah, some of them.
some of them are use substitution, right? So you recognize that things like the sine theta, cosine theta, and here's sine theta, cosine theta, those can be done with use substitution, as can the cosine at the end. I mean, not with use substitution, but it can be done. The only one that's really causing us problems is this one at the beginning. Agreed? So what could we do to fix this one at the beginning? This is a Calc 2 question, right?
Can we put it with the sine squared cosine
Oh, don't we
theta?
have to?
Sine squared cosine theta? How? What do you have in mind? This is one of those integration techniques from Calc 2.
Don't you have to do a substitution like a trig identity?
I think that's a good idea.
Like separate it out from sine squared.
Yes.
Calculator idea sounds awesome.
That is exactly the idea.
Sine squared is.
So, all right, let's actually pause then on this slide and let's just look at that piece of it because that's the piece that's causing problems, right? We know we can handle all of this right here. Agreed? Everything from here over, we're good to go. We can either use U substitution or integrate it directly. It's the sine cubed that I want to deal with. And I don't even care about the negative 64 because it's just a constant at the beginning, of course, as well. So let's talk about what happens when we have the sine cubed. Okay, so what you mentioned, Caleb, is exactly right. We're going to separate it as sine of theta and sine squared of theta. Sine squared of theta has a trig identity that we can use. What will it equal?
1 plus cosine minus cosine 2 theta all over 2.
Right, 1 minus cosine squared, 1 minus cosine squared of theta.
Those 2 theta.
You're thinking about a double angle. We don't have a double angle, we have a squared. I'm just using the Pythagorean identity.
Okay.
So, or you may be thinking of a different identity in fact as well, I'm not sure. There are some double angle identities that you can use. This one's not a double angle. And I'm not promising this is the only way to do this either. But okay, so take a look here. Then I've got sine of theta minus cosine squared theta sine theta, right? The first piece now I can integrate no problem, yes? How about the second one?
U sub.
We can use U substitution on that one as well now, right? So we have U substitution in several places. Let's actually find this piece since I'm already in the middle of this piece, and then we'll go back and pick up the last 3 other pieces that we needed to do from the previous slide when we're done with this one, all right? So this piece of integration, what do you get? Right, negative cosine of theta. The second piece, as y'all mentioned, is a U substitution where U equals what? Cosine of theta. So I've got negative there, there's my integral. Cosine squared would then be U squared. And then the du over here is what? Negative sine. So that's actually going to change the sign here as well to positive, right? Because I need the negative, I need the sine, and I need the d theta to be replaced with the du. So this will end up giving me the negative cosine of theta plus the integral of u squared would be u cubed over 3, but u is cosine of theta, so this is 1/3 cosine cubed theta. Okay, is that all right?
Yes.
Okay, that's only one of the 4 pieces. The other 3 of the 4 pieces on the other slide over here had the same U substitution, at least the 2 in the middle. So let's take the 2 in the middle, okay, and let's do them next.
We need to put the negative 64 in.
Yes, thank you very much. I already lost my negative 64. Not a bad thing to do. I mean, not a good thing to do. It is a bad thing to do. If I just put it at the beginning, we wouldn't have lost it, would we? And I left off my limits of integration, so I don't actually need a plus c here on the end either. It was 0 to pi, so we'll do all the limits of integration in a moment. So all of this has 64 in here. So I have negative 64, and I have 64 over 3. It was negative, positive. My signs changed, didn't I? Because it was negative 64. You're right. So 64 cosine theta minus 64 thirds cosine cubed theta. So far, so good? All right. Need some more space. So we want the integral then of negative 16 sine theta cosine theta plus 64 sine squared theta cosine theta d theta. This is the pieces that will need the U substitution. What will U be here? Sine of theta. And then du would be cosine theta d theta. So I have the integral of negative 16u plus 64u squared. The cosine thetas are getting to be replaced by the du's with the d theta at the end. All right, so integral of negative 16u would be what? Negative 8u squared. And then 64u squared? 64 over 3u cubed. And our u is sine theta. So this is negative 8 sine squared theta plus 64 thirds sine cubed theta. And then we had one more integral at the very end that we didn't do, which was simply 8 cosine of theta d theta. So let's do that piece of it real quick, and then we can put all three of these together. That's 8 what? I think it's positive, isn't it? Antiderivative of cosine is sine. That look okay? All right, so the three pieces that we have, one of them's right here. The second one was right here. And the last one was positive 8 sine theta. And none of them combine, right? They're all different. What's the last thing I need to do then? Yeah, the limits of integration. The limits of integration are at pi halves and at 0, which are actually really nice values. Why? Why are those going to be so nice? We're either getting zeros or ones for everything, right? Because we're at the quadrantal angles. So let's do it for pi over 4 first. So when you're, pi over 2 first. When you're at pi over 2, which of the two are 0? Is it sine or is it cosine? Its sine is 0 and the other ones are 1. So to start with, I've got 64 minus 64 over 3. And then I've got 0 here in the middle for the 8 sine squared, 0 for the 64 over 3 sine cubed, and 0 for the 8 sine theta at the end. Then I'm going to plug in 0, and when I plug in 0, the cosine thetas are 0. So I get the two zeros at the beginning, 0 minus 0. And then I get all the same values for the coefficients. So negative 8, because sine values are all 1, plus 64 over 3, and plus 8. All right, so 64 minus 64 thirds. Let's see, minus another 64 thirds, right? And minus 8. Did I catch them all? No, I missed one, didn't I?
Plus 8.
Oh, how about
But
this?
it's plus 8 minus 8.
Yeah, let me just mark those out to begin with then. That work? So what happens when we have 64 minus 64 thirds minus 64 thirds? What do we get? Okay. So 64 minus that. Yes, Nidra, did I make a mistake? Where did I get the first part? These numbers? Right here? I plugged in the pi over 2. When you plug in pi over 2 into cosine, did we plug it in backwards, guys? Did I plug them in backwards? Hang on. I did. I've got them backwards. Thank you, Nidra. We'll switch them. I can do that pretty quick, though. I did. I got them backwards. Look at that. Oops. Didn't I?
Cosine of pi over 2.
Pi over 2 first, right?
Yeah. But when you plug in cosine of pi over 2, you get 0. I had them backwards. Cosine of pi over 2 is 0. The sine of pi over 2 is the, yeah, I plugged them in backwards is what I was doing. All right, so let's fix it. Okay. All right, let's try one more time. 64 thirds. I still have the same numbers. I'm going to end up with the same value with the opposite signs of what I was trying to give you before. So 64 over 3 minus 64 and then plus 64 over 3, right? All right, I think we got it all there. So we need an answer to this value now. Caleb, did your calculator give you one?
I'm sorry, I did it different than you guys.
Okay, that's all right. Somebody evaluate for us real quick.
Negative 64.
It is negative 64 thirds.
That's what I got.
That's correct, yeah. Yep, very good. Okay, homework for this section. On page, oh, did I write it down already last time? I did, you're right. I put it on the board. Okay, very good. Of course I can, Tally. All right, this is page 1001. Numbers 1, 4, 6, 11, 16, 19, 22, 26, 30, 33, and 36.